My name is Isabelle Panet, and I will briefly introduce our paper detecting preseismic signals in grace gravity solutions application to the 2011 Tohoku earthquake. So retrieving preseismic signals before the occurrence of a rupture is a key multidisciplinary challenge of earth sciences. At timescales from days to decades, deep and shallow deformation transients before great earthquakes have been evidenced from retrospective analyses of geodetic and seismic data. All these observations suggest interactions between deep and shallow deformation processes at different timescales before an earthquake occurs. However, our knowledge of the full spectrum of transient deformations of the pooling slab at depths remains mostly beyond the reach of these geodetic and seismic data. With its unique sensitivity to mass redistributions at all depths, satellite measurements of the time variations of the Earth's gravity field can overcome an observational gap to detect and characterize the full spectrum of deformations of the subducted slab. And this is how we have mapped in a previous study an anomalous gravity gradient signals in the months before the 2011 Tohoku earthquake, likely caused by a deep and broad slab deformation, which could provide favorable conditions for the occurrence of the rupture, as this deformation would migrate to the surface, with also a similar observation before the Maule earthquake by Bouy et al. EPSL. So in this context, our objective is to set up a method here for the early identification of preseismic gravity signals in satellite gravity data before the rupture occurs in view of a systematic monitoring of deep mass redistribution at subduction zones. So taking the example of the Tohoku earthquake, we ask ourselves, can we identify its preseismic signal as a unique feature in a global systematic analysis? For that, we first carry out methodological developments in the analysis of the space-time variations of the gravity field, where we use gravity gradients to characterize the spatial variations, and we improve our analysis in order to obtain an enhanced angular resolution of the gravity gradients around a direction of interest, here the direction of plate boundaries, in order to extract signals closely aligned with the subduction boundary as a geological constraint. And then we extract the fast signals at subannual timescales to build global anomaly maps. In the second step, we set up a method to objectively compare two such global anomaly maps that have been obtained from different grace gravity models and test the sensitivity of the signals to the ocean mass model, which is used in the processing of the grace data, and to the choice of a grace solution. So here we have an example where we compare the red signal A from a first global anomaly map with the blue signal B in the second global anomaly map, and they have an overlap which is marked in green, and we define two parameters, K, which gives the relative intensity difference of these two signals in their overlapping zone, and S, which gives a fraction of the total magnitude of a signal, A or B, which is comprised in the overlap zone. So using threshold on the K and S parameters, which are computed for each signal, we can select consistent signals in two different grace gravity solutions, or consistent signals with or without restoring the ocean mass model, or a combination of the two. And so this is what we do. First on the GRGSO3 grace geoid models, and we compare such model with or without restoration of the ocean mass model to select signals which are poorly sensitive to this ocean model. And so in February 2011, we identify only a few large amplitude signals left, and one of them has a dipolar structure along the plate boundary around Japan, which is typical of a solid Earth source. And then we make statistics considering the whole time series from July 2004 to February 2011, and we make the statistic of the magnitude of the signals all over the globe or over the oceanic domain to show that the pre-Tohoku anomaly reach very high percentiles, and so their magnitude is very anomalous. both globally or over the ocean, and whatever the K and S parameters. And then we perform comparison with the second grace gravity model, CSR06, to show that this pre-Tohoku signal is among the most consistent signals between the two, and it is also highly anomalous in magnitude in the CSR solution. So this systematic analysis is able to detect the uniqueness of the pre-Tohoku signal before the occurrence of the event. It is unique because of its magnitude and its dipolar structure, confirming its preseismic nature. It shows that we can identify before a rupture anomalous gravity gradient variation along the subduction boundary, which are likely to reflect processes associated with subducted slab deformation, which offers perspectives for systematic monitoring of subduction zones worldwide, and with also the example of the Maole earthquake in the EPSL 2022 paper by Bouy et al. Thank you.